Hey y'all, welcome back. On tonight's homework, we are going to be answering all kinds of questions related to derivatives, their graphs, second derivatives. We'll probably be using some first and second derivative tests. But really, overall, we're just trying to analyze these graphs and the connections between f, f prime, and f double prime. Number one says, find the critical points of the function. So critical points are going to be any x value that makes either the derivative equal 0 or undefined. So part A has a quartic function here, and we're going to go ahead and differentiate it. So f prime is going to be equal to 4x cubed minus 4x squared. And so to find the critical points, we need to set this equal to 0 and then solve for x. Cubic functions are never undefined, so we don't really need to worry about that component to it. But let's go ahead and set this equal to 0. Factor out of 4x squared. And then solve, set each one of these two factors equal to 0 and solve them both. We're going to get x equals 0 and x equals 1. Now, to determine what's going on at these x values, we are going to have to create a little number line chart, a little sign chart here for f prime. We're going to put 0 and 1 here and try to figure out in each of these intervals whether or not the function's positive or negative. And that's going to help us determine whether or not these points are relative maxima, which is where the derivative, or f prime, goes from being positive to negative, relative minima, which is when f prime goes from being negative to positive, or neither, which if it's neither, there's no sign change. Okay, so if I plug in a number like, say, -1, now this 4x squared, this first factor here, that's always going to be 0 or positive because squaring a number, when you multiply a number by itself, it's always going to be positive unless it's 0, in which case it's 0. But it'll never be negative is kind of the point. And so any number that we plug in here, we really just need to worry about the x minus 1. We can safely ignore the 4x squared when trying to determine if these intervals are positive or negative. Now, so if I plug in a number like -5, the first interval will be negative. If I plug in a number like 0.5, 0.5 minus 1 is negative. However, if I plug in a number like 10, 10 minus 1 is positive. So at x equals 0, it is neither a max or a min because there is no sign change. And at x equals 1, since it's going from negative to positive, f will have a slope that's negative followed by a positive slope. Right here we've got a minimum value. Part B gives us f prime. So we actually don't have to find f prime. F prime's already given. And so we can jump straight to the critical points. X equals 3 and x equals -2. Those are our critical points. And so we want to classify each of these in the same way that we did the last problem. So we've got -2, we've got 3. Plugging in a number like -5 is going to give me a negative number times a negative number, which is positive. If I plug in a number like 0, I get negative times a positive, which is negative. And if I plug in a number like 5, 5 minus 3 is going to be positive. 5 plus 2 was positive. A positive times a positive is positive. So if our f prime, which is what we're working with here, goes from being positive to negative, we will have a relative maximum. And if that was at -2, not at 3. If the function goes from being negative to positive, we have a relative minimum, and that is happening at 3. All right, so there's A and B. Number 2 has a graph of f prime here. It says the graph of f prime, which is the derivative of f, is shown above. F and f prime are both defined between -10 and 10. A says list the critical points of f. So critical points of f are going to be places where f prime is either 0 or undefined. And the only places that we see here, don't really see any places where it's undefined, but we do see locations where it is 0. So we're going to pick up -7, -1, 4, and 8. Those are going to be our critical points of f. Okay, critical points of f, like we said above, are where the derivative is either 0 or undefined. B says, for what values of x is f increasing? So if f is increasing, that means f prime is positive. So if I'm looking at the graph of f prime, we can see that f prime is positive everywhere the graph is above the x-axis. So that's going to be up here and also over here. We're going to have two intervals, one of which is between -7 and -1, and the other one's between 4 and 8. Letter C. I guess I should stay consistent with my coloring, huh? What do you think? Let's rewrite that. -7 to -1 and 4 to 8. Okay, letter C. For what values of x is f decreasing? Okay, so if f is decreasing, that means that f prime is negative. So we're looking for places on the graph where the function f prime is below the x-axis. And we see that here, we see that here, and we see that here. So we're going to have three separate intervals here. Let me zoom out so I can see as I write. We've got one between -10 and -7. We've got another interval between -1 and 4, and finally an interval between 8 and 10. D says at what values of x does f have a local maximum? Okay, so for f to have a local maximum, f prime needs to go from being positive to negative. All right, so it's going to happen at one of those x-intercepts, or maybe multiple ones, but we're looking for where the graph goes from positive to negative. And we can see that here at -1, the function, the f prime, is changing from being positive to negative. And we also see that occurring at x equals 8. So in both of these cases, f prime is going from being positive to negative, so f should have a local maximum. So we're going to say x equals -1 and x equals 8. E says at what values of x, if any, does f have a local minimum? Okay, so to have a local minimum, let me space this out so I can have a little bit of space here. F prime needs to go from being negative to positive. And my graph up here is getting a little crowded up here, but I think we'll be okay. So we're looking for places where f prime is starting below the x-axis and moves above the x-axis. And so we're going to see that here at -7 and also here at 4, where the graph f prime goes from being negative to positive. So -7 and 4 will be the two x values. Number 3, we have this gigantic table. And part A says list the critical points of f and g. Okay, so for f, we're looking for where f prime is 0, and we see that's happening here when x is -1. Let's see where x is 0 again, or f of x is 0 here, so that's going to be at 0. It does not exist at 1, so we'll go ahead and list that as well. For g, we're looking for where that is 0 undefined, where f prime is. So let's see here. It's going to be 0 at 0. And it looks like that's it. That's going to be the only critical point for g. B says list the coordinates of each relative extremum on the graph of f and g. So we're going to be looking at these critical points to see if we have a local maximum or minimum. Again, this is going to depend on whether f prime is changing sign or not. So like for instance, at x equals 0, I'm looking right here, f prime does not change sign. Okay, so that's not going to be a relative extreme. It's going to be like if we were to write it up here, it would be in the neither category, kind of like this answer right here. Neither a max or a min. Still critical point, but just not an extreme. So if I look at the next one, where x is 0, right here, we can see that f prime is changing from being negative to positive. So if the slope is starting from being negative to positive, we know that's a local minimum. Okay, so we've got a minimum at x equals 0. The y-coordinate here is going to be f of 0. Right here, that's 2. Okay, so let's let me make this very clear. This is for function f. Got a minimum at 0, 2. And then let's see what's happening when f prime of 1, it says it doesn't exist. Do we have a sign change? And in fact, we do have a sign change. It's changing from being positive to negative. So we've got a local maximum there. So we got a local maximum at, let's see, the x value is 1 and the y value is 4. For function g, there's only one critical point to check, and that's going to be at x equals 0. So we're really just looking for the sign change on g prime. And we see it's going from being positive to negative, so we've got a local maximum. The x is 0, the y is 3. I'm circling it right here. That is g of 0. So I'm going to erase some of this stuff because this is getting kind of messy up here, but there are your answers for A and B. Number 4 says find the points of inflection to determine the intervals which the function is concave up or concave down. So we are going to find the second derivative of each one of these functions, create a sign chart, and analyze the signs in each interval. So let's start with the first one. F prime would be negative 6x squared. So f double prime would be negative 12x. All right, this is only going to have one critical value. All right, if I set that equal to 0, solve for x, I just get x equals 0. So my number line is just going to have 0 on it. And if I plug in a negative number, a negative times a negative is positive. If I plug in a positive number, negative 12 times any positive is going to be negative. So we do have an inflection point here. Okay, so we've got an inflection point at 0. Let's see, how should I write this? I'm going to make a little answer box right here for me. I'm going to say it's concave up between negative infinity and 0, concave down between 0 and infinity, and then I've got an inflection point, or maybe I should say a point of inflection. So point of inflection at x equals 0. And that's because the concavity changes there. For letter B, the first derivative, g prime, will be 4x cubed minus 6x squared minus 72x. G double prime would be 12x squared minus 12x minus 72. So what I need to do is set that equal to 0 and solve it to find my subcritical values. 12x squared minus 12x minus 72 equals 0. 72 is divisible by 12. I believe, let me just do a little mental math here. Yeah, it's 6. So if I divide everything by 12, I'll get x squared minus x minus 6 equals 0. In factored form, that'd be x minus 3 times x plus 2. And so now I can find my two critical values, my subcritical values are going to be at 3 and negative 2. So I'm going to create my little number line chart here. Really didn't leave myself much room for this one, huh? I'll scoot all this over a little bit. Yeah, that's good enough. You know what? What if I just scoot everything over a little bit? Yeah, there we go. Okay, that's much better. All right, so I'm going to create my little number, my sign chart here, and this is for F, or no, not F, sorry, G double prime. Didn't label the last one either, F double prime. So we've got -2, we've got 3, and then we're going to start testing values. If I plug in a number like -5, I'm going to get a negative times a negative, which is positive. Plugging in a number like 0 gives me a negative times a positive, which is negative. And finally, plugging in a number like 10 gives me a positive. Okay, so we're going to be concave up on two intervals, -infinity to -2 and 3 to infinity. We're going to be concave down in that middle interval between -2 and 3. And we have we actually have 2 points of inflection because we have 2 sign changes here. So we got a point of inflection at x equals -2 and at x equals 3. Should have given y'all more room for that one, I think. Oh well. Number 5. When does this graph have a point of inflection? So we're going to approach this just like we did number 4. We're going to find the second derivative. We're going to create a sign chart, and we're going to look for the sign to change. So that is f prime. So f double prime is 3x squared minus 9. Setting that equal to 0. To find my subcritical values is going to give me 3x squared equals 9. Divide both sides by 3. And then take the square root, gives me x equals plus or minus root 3. So those are my subcritical values. Those are the ones that I'm going to place on the number line. And if we have a sign change at any of these places, then there'll be points of inflection there. So if I plug in like -10, now hold up here. If I plug in like -10, squared would be 100. We got 300 minus 9. That's positive. Plugging in 0 gives me -9, so that's going to be negative. And plugging in something like 10 is going to be positive again. So we have 2 points of inflection. We have a point of inflection at x equals root 3 and one at x equals -root 3. The graph will be concave up on any intervals where the second derivative is positive. So that's going to be in between -infinity and -root 3, but also between root 3 and infinity. Number 6 gives us the second derivative and wants to know where the points of inflection are. It's kind of the same question, except they gave us f double prime. So since they gave us f double prime, we can just jump straight to the number line. We need to find our critical values. We're going to have one at x equals 0. We're going to have one at x equals 3 and at x equals -4. So 0, 3, -4. We're going to have 4 intervals to test. So plugging in a number like -10, now this x squared will always be positive, and actually so will the x plus 4 to the 4th. So those will always be positive, so when we're checking these signs, we only need to be looking at x minus 3. So if I plug in -10, -10 minus 3 is negative. Plugging in something like -1, -1 minus 3 is also negative. By the way, we've got a root here, -4, with even multiplicity. Okay, anytime you get that even multiplicity, you're going to expect the sign doesn't change. But you want to test it anyway, just to make sure. If I plug in 1 minus 3, is negative again? I suppose so, because, we got less even multiplicity on that 0 as well. And then, 3 is just a singleton, so I'm going to expect the sign to change here. If I plug in 5 minus 3 is in fact positive. So there's actually only 1 point of inflection here, and that's at x equals 3. Where is the graph concave down? Well, it's concave down pretty much everywhere except for where x is greater than 3. So I'm just going to say, you can either say x is less than 3, or you could say from -infinity to 3. Either way, one of these is fine. I'll take either one. Number 7 wants to know, where's this increasing and concave up? So not only do we need f prime to be positive, but we also need f double prime to be positive. So we are going to find where we're going to do that sign chart, not only for f prime, but also for f double prime. The follow-up question, just to kind of, since it's very similar here, wants to know when is f prime negative? Oh, okay. So f prime negative, that means f prime is less than 0. Increasing means f double prime is positive. Okay, that's almost the same question as A. It's just the f prime's different. Interesting. Okay, so let's find our two derivatives here. We'll start with f prime. Using the power rule, we're going to get 20x cubed minus 5x to the fourth. I am going to need to find the critical values here, so I might as well go ahead and do that now. Setting this equal to 0. I can solve it by, first, let's just, let's factor out a 5x cubed. Make this a little simpler. Times 4 minus x. So we're going to get two critical values. One at x equals 0 and one at x equals 4. So this is going to be my number line chart for f prime. We still need to check f double prime, but we'll do that afterwards. Uh-oh, lost my window there. There we go. So yeah, we've got one at 0, one at 4. Plugging in a negative number is going to give me a negative, like if it's -1, for instance, a negative number times a positive is negative. Plugging in 1 gives me a positive times a positive, which is positive. And plugging in something like 5 gives me a positive times a negative, which is negative. Okay, so we'll come back to this to answer the question, but we're going to need the second derivative anyway, so I'm going to just kind of bypass this for a second. And now let's find the second derivative. So the second derivative is going to be using the power rule on this one right here. This is the one I'm looking at. I'm going to get 60x squared minus 20x cubed. So setting that equal to 0 and factoring, I'm going to get two values, x equals 0 and x equals 3. I'm going to have to I'm going to need a little bit more space here. Can I squeeze it in there? No, I don't think so. I'm just going to go ahead and draw f double prime here with 0 and 3. Now I'm going to be plugging into the second derivative here. And if I plug in a number like -5, now this 20x squared right here will, I'll just erase something. The 20x squared here is always going to be positive, so I'm going to ignore that when figuring out my signs. Plugging in -3 is going to, 3 minus -3 would be positive. Plugging in 1, 3 minus 1, also positive. And then finally, if I plug in 5, 3 minus 5 is negative. Okay, so to answer A, we're looking for the interval where f prime is positive. So we can see that that is in between 0 and 4. And concave up. That's where the second derivative is positive, and that's going to be in this interval. So the interval where both of these are true is going to be in between 0 and 3. Now, part B wants to know when the first derivative is negative. So that's going to be in this interval and in this interval. Let me clean that up a little bit. Okay, so that's where f prime is negative, but I also want for where f double prime is positive. And f double prime is positive, where I've got the yellow highlight already. It's the same location as it was before. So, above 4, even though f prime is negative, I'm not going to want that interval. I just want the interval between -infinity and 0. So in order for the interval to be the answer to either one of these questions, A or B, you've got to satisfy both the requirements for f prime and f double prime. Number 8. Now in this one, what's different here is that they're giving us the derivative of f rather than f itself. And the first question is asking, when is f increasing and concave down? So F increasing, we're looking for where F is positive, or F prime, and concave down, we're looking for where F double prime is negative. So let's find the zeros here, the critical points. And they already gave us F prime, so we don't actually need to differentiate that first time. We can see that we've got two critical values, one at -1 and then one at 3/2. So I'm going to construct my number line here for F prime. And maybe I'll make sure that all this gets sectioned off so we don't get confused there. And I'm going to place -1 on here. I'm also going to place 3/2. So we've got 3 intervals to check here. And if I plug in a number like -2, I'm going to get a negative value. The x plus 1 squared, this is always going to be positive. And cubing something is not going to change the sign. So I'm really just looking at 2x minus 3. And if I plug in a number like -2 or -10, that is going to be negative. If I plug in a number like 0, 2 times 0 minus 3 is also negative. And then finally, if I plug in a number like 10, I'm going to get a positive number. Okay, so it's going to be increasing when x is greater than 3/2. Now let's find the second derivative. Now this is going to be a little challenging because we've got a, we can't just go ahead and use power rule here. We're going to use power rule a little bit, but really what we're going to be using is the product rule, which we have not used in quite a while, and a little chain rule to go along with it. So let's find that second derivative. So the second derivative, in terms of x, make sure my notation's okay here, is f prime g plus fg prime. So the derivative of x plus 1 squared is going to be 2 times x plus 1. Now, normally I would use chain rule here, but the derivative of x plus 1 is just 1, so I'm not going to write anything, times 2x minus 3 cubed plus the first expression, x plus 1 squared, times the derivative of the second, so times 3, I'm sorry, yeah, no, I was right there, times 3 times 2x minus 3 squared times the derivative of 2x minus 3, which is 2. Okay, now this looks like it's going to be a pretty tough equation to set equal to 0 because we don't have it in factored form yet. But luckily it's not, I mean, it is challenging. I don't want to sugarcoat it here, but it's not as bad as it looks. Okay, if I just examine the fact that I've got a sum of 2 expressions here, so I've got this expression plus this expression, I can factor out a GCF, which is going to be more than just a single term. It's going to be a whole expression. So what I'm going to be looking for are any factors that are present in both of these individual pieces to factor out as a GCF. So like, for example here, notice there is a factor of 2 in both of these expressions. So I can factor out a 2 as part of my GCF. Okay. I also see that I have a single x plus 1 present in both expressions. Now in the second expression, it's x plus 1 squared, so I'll have an x plus 1 left over, but I can factor out an x plus 1 and from both of these. Similarly, I can factor out a 2x minus 3, and actually I can factor out 2 of them. I can factor out a 2x minus 3 squared. So I will be left with a single 2x minus 3 on the first expression, but overall I can factor out 2x minus 3 squared. Now that's going to leave me with everything that didn't get factored out. In that first expression, I'm left with just a single 2x minus 3. And in the second expression, I'm left with a 3 and an x plus 1. So I have 3 times x plus 1. Simplifying everything that I have there in brackets, I'm leaving the rest of this the same. Really just requires combining like terms, a little bit of distributive property. I've got 2x plus 3x is 5x. And then negative 3 plus 3 is just 0. So it's just times 5x. So now I have f double prime in factored form. And so I can find my subcritical values. I'm going to have one at negative 1. I'll have one at 3/2, and I'll have one at 0. So those are going to be the three numbers I place on my sign chart. Negative 1, 0, and 3/2. Now I'm going to plug in some values to see whether or not this function is positive or negative. So if I plug in a number like negative 5, for instance, and really I'm just going to be focusing in on x plus 1 and 5x. And the reason for that is squaring something like we've got here is always going to be positive, and 2 obviously is always going to be positive. So multiplying by either one of those two factors will never change the sign of the number. So if I plug in a number like negative 10, I'll get a negative times a negative, which is positive. Okay, if I plug in a number like negative 0.5, then let's see, what would that be? That would be a positive times a negative is negative. Then plugging in a number, like 1 is going to give me 2 times 5. That's going to be positive. And then if I plug in a number like 10, that'll always also be positive. Okay, so I'm looking for where f is increasing, and so f is increasing when f prime is positive, so that's going to be here. And f double prime is concave down, so that's going to be where the second derivative is negative. So notice that there is going to be no overlap here, right? The f is increasing after 1.5, but is only concave down between negative 1 and 0. So unfortunately, this never happens. Don't you just hate that? You do all that work to find out that there just isn't an answer. But I think there's going to be an answer to B, because for B, we're looking for where f prime is negative, which happens all over here, and also where f double prime is negative, which is the same place where it's concave down. And so there is an overlap in those two intervals, and that overlap is going to be between negative 1 and 0. So there's 8b. Number 9 says, where does the graph of f have a point of inflection? Okay, so that's where the concavity changed. Now, for this first one, we're going to have to just kind of estimate. Okay, it looks like the concavity is changing right here. So we'll just say, for the sake of argument, that yeah, the point of inflection is at 1. It kind of looks like it. We don't have really enough information for sure to say, but I think that's a fair enough guess. Just compared to all the other points. So we're going to be concave up from negative infinity to 1. We're going to be concave down from 1 to infinity. And we have a point of inflection at x equals 1. Now that's the graph of f. And you can usually do the old visual test there. It may be a little bit more complicated if you really need to know exactly where that point of inflection is. You might have to go back and find the equation, do the second derivative and all that like we've been doing. But for right now, just for doing the old eyeball test, I think that's good enough. Okay, for B, now let's be clear here. F is concave up when f double prime is positive. That means the slope of f prime has to be positive. Okay, so the slope of f prime is positive here and here. Okay, so it's concave up there and there. It's concave down here and here. And the points of inflection will exist when the sign of f double prime changes. So that's going to be at these two, or actually three, relative extremes. So it's going to be concave up. F is concave up from, looks like negative 1.5 to 0, but also from 2 to infinity. It's concave down between negative infinity and negative, was that actually a point, or was that, oh, no, that was a point. So I apologize. That's negative 2. Let's fix that. Negative 2 to 0, and from 2 to infinity. Yeah, so concave down from negative infinity to negative 2, and from 0 to 2. And then we have 3 points of inflection. We're going to have one at x equals negative 2, one at x equals 0, and at x equals 2. All right, let's look at letter C. This is f prime. Okay, so again, where it's concave up is going to be where the slope of f prime is positive. So it's going to be concave up here, but it's going to be concave down here and here. We are probably going to want to set those two intervals, state those two intervals separately, though. Now, notice there's no sign change at x equals 1, so there's no point of inflection there. There's only going to be a point of inflection at 2. So we've got, I'm going to list these intervals separately. Well, concave up, there's only one interval, so that's at 2, from 2 to infinity. It's going to be concave down from negative infinity to 1, and also from 1 to 2. Okay, this is not continuous, so I don't want to join those two intervals. I've got a single point of inflection at x equals 2. Letter D. Okay, so this is a graph of f prime again. So I'm decreasing, or f double prime is negative here, and f double prime is going to be positive when the slope of f prime is positive, so here and here. I'm going to have 2 points of inflection because the sign of this slope is changing at both plus or minus 1. So it's going to be concave up, or f is concave up, between negative infinity and 1, but also between 1 and infinity. It'll be concave down between negative 1 and 1. Uh-oh, I think I left off a negative there. Yeah, negative 1 and 1. And our points of inflection are going to be at x equals negative 1 and x equals positive 1. All right, last but not least, we have two graphs that are f double prime. Okay, this is actually going to be, should be the easiest case. Okay, because concave up means that f double prime is positive. So it's going to be concave up when the f double prime is above the x-axis, and will be concave down, or f will be concave down when f double prime is below the x-axis. And then we'll have those points of inflection when f double prime changes sign. So here we'll have them anywhere we have these x-intercepts where the graph crosses over. So f is going to be concave up between negative 2 and 0, but also 2 to infinity. It'll be concave down between negative infinity, negative 2, and 0 to 2. And I'll have points of inflection at x equals negative 2, 0, and positive 2. Am I missing anything? No, that's all it's asking for. Okay, letter F. It's also a second derivative graph, which is positive in between negative 3 and 2, and negative outside of that interval. I'm going to have points of inflection at these x-intercepts where the sign of f double prime changes. So f will be concave up in between negative 3 and 2, concave down between negative infinity, negative 3, and also between 2 and infinity. And then I'll have 2 points of inflection here, one at x equals negative 3, and the other one at x equals 2. Whew, all right. This was quite the homework. But yeah, I guess that about sums it up. We're done here. So yeah, as always, y'all, Please let me know if you have any questions. I know we had some rather challenging problems on here. So if you're still a little confused, please just reach out and I'll try to explain it a little bit better. But otherwise, y'all have a great night and I'll see you next time.